Okay, let's dive right into this. Today, we are going to completely deconstruct the OmniRAG engine, and we're going to do it specifically through the pragmatic, systems thinking lens of a senior software architect. If you've ever tried to build a retrieval augmented generation, or RAG, system that actually has to survive contact with real-world messy production data, well, you know it is rarely as simple as those 5-minute tutorials make it look. So this explainer is going to give you the exact architectural blueprint of a Go-based system designed to solve those very real production headaches.
Here is the blueprint for our system design review today. We'll be covering fixing real-world RAG, decoupling data and intelligence, navigating the vector store matrix, taking a look under the technical hood, and finally, mapping out the multi-agent roadmap.
All right, Section 1, Fixing Real-World RAG, the foundational problem.
As an architect, you always have to start by asking the hard questions, right? Like, why do out-of-the-box RAG setups just fail so spectacularly on real-world data? I mean, we've all seen it. A basic RAG script works flawlessly in a pristine Jupyter notebook, but the second you deploy it against a living production database, it completely falls apart. And usually, that's because standard setups force these super intrusive database schema migrations, or they demand heavy back-end reindexing of your live transactional data. And let's be real, a schema migration on a Friday afternoon is literally a recipe for tears. From an operational standpoint, it just introduces massive, massive risk.
So, the crucial point here is that the OmniRAG design philosophy fundamentally respects your primary transactional database. In the current implementations, it treats MongoDB as the absolute untouched source of truth. It simply layers on top of it. By choosing not to alter those core data structures, you completely sidestep the operational nightmare of migrating live schemas just to appease an AI model.
Moving on to Section 2, Decoupling Data and Intelligence. Let's talk about physical separation. This brings us to a really foundational concept in the OmniRAG architecture, zero data alteration. This is the philosophy of working directly on raw, unpadded text segments. You literally do not mutate the source data. Instead, you shift all of that intelligence and routing logic entirely to the orchestration layer. This non-intrusive handling means your primary data remains totally pristine. Meanwhile, deterministic keyword protection, using pre-filtering at the vector level, drastically reduces embedding drift on those really tricky short-tail keyword searches.
And this brilliantly illustrates how that physical separation actually plays out. You start with MongoDB acting as the ultimate source of truth. The ingest service reads that content, reaches down to Alma to grab the embeddings, and then upserts those vectors into a completely separate vector store, so something like ChromaDB, Qdrant, or Pinecone. Meanwhile, down in the retrieval phase, the orchestrator sits right in the middle. It acts as the brain, routing data, applying adaptive filters, and deciding whether to send the final grounded prompt out to a cloud model like Claude or a local Alma model. Let's actually break that exact pipeline sequence down into its 5 steps. First, you read from MongoDB. Second, you generate the vector embeddings using Alama. Third, you upsert those vectors into your dedicated index. Fourth, and this is absolutely where the magic happens, you orchestrate the retrieval. Think of this orchestrator as a highly intelligent traffic cop. It's applying adaptive filters and semantic fallbacks before the data ever even reaches the LLM. And finally, step 5, it generates a highly grounded prompt for the generation model to actually answer.
Okay, Section 3, the vector store matrix. The classic buy versus build dilemma. When evaluating the database decisions for your vector store, you really have to weigh the trade-offs. Let's look at some dedicated native vector engines. Take Qdrant. Built in Rust, its superpower is in-graph filtering, which keeps latency down around a blazing 12 milliseconds for setups under 100 million vectors. But, the catch is a smaller plugin ecosystem. Then you have Milvus, built for multi-billion vector scaling, but that brings extreme infrastructure overhead requiring some heavy DevOps tuning. Or consider Pinecone, a closed-source serverless option that offers this great zero-ops experience, but traps you in hard cloud vendor lock-in with some aggressive usage-based pricing. You also have to weigh those dedicated engines against traditional database extensions. For example, using an extension like pgvector inside Postgres is incredibly tempting because it gives you unified SQL relational joins right alongside your vector searches. But if you have high concurrent vector queries, you can easily saturate your server CPU and RAM, which suddenly slows down your primary transactional tables. On the flip side, a native engine like Weaviate will automate vectorization natively right inside the database, but it comes with a significantly higher memory footprint. As an architect, you're constantly balancing that operational simplicity against raw performance and resource costs.
Now, what's really interesting here is how OmniRAG implements one of these specific engines to guarantee retrieval accuracy. This is the quadrant-backed architecture. Notice how the pipeline explicitly applies payload text filtering between the retrieve service and quadrant. It is executing strict metadata checks against the content field during the vector graph traversal. That ensures incredibly high deterministic accuracy for exact keyword matches before it even attempts to run a fuzzy semantic stretch.
But what happens if a user searches for an abstract concept rather than an exact keyword? Well, that's where dynamic failure fallback kicks in. This essentially acts as an architectural safety net. If that strict payload filter we just talked about returns 0 string matches, the system automatically drops those constraints and seamlessly shifts over to pure semantic vector math. It bridges the gap between localized short keyword searches and broad abstract queries automatically, ensuring high recall without the user ever noticing a hiccup.
Section 4. Under the technical hood. Let's look at the microservices and infrastructure. To really see the flexibility of this design in action, we can analyze the Pinecone-backed implementation, which is specifically engineered for ingesting full PDFs and books. It actually extends the standard pattern. We start with an upload UI capturing the raw PDFs, which are then passed into the ingestion service and stored directly as raw files in MongoDB GridFS, keeping that source of truth fully intact.
Breaking that Pinecone implementation down a bit further, it chunks the documents page by page using LangChain Go, extracts the embeddings using Alama's nomic embed text model, and then upserts them directly into a managed Pinecone index. On the retrieval side, it serves a server-sent events, or SSE, streaming API. And brilliantly, the generation backend selects between Anthropic's Claude or local Alama based on your config, completely implementing a credit balance guard to fall back cleanly if your cloud API credits happen to run out.
So zooming out for a second, here is a rapid-fire review of the tech stack powering all of this. The backend runs on lightweight Go HTTP services, which provides incredible concurrency and a really small orchestration surface. MongoDB is your primary store. You have your pick of ChromaDB, Quadrant, or Pinecone for the vectors. Embeddings are handled entirely locally by Alama, and generation can easily swap between a cloud giant like Claude or local models like Gemma 4. It's also worth noting that because Alama is customizable, you can scale your local generation models from lightweight 2 billion parameter models on a standard laptop all the way up to 13 billion plus parameter models if you have dedicated Apple Silicon or high-end GPUs.
Finally, Section 5, the multi-agent roadmap and our architectural evolution. Let's move to the roadmap and see how this builds over time. Right now, version 1.0.0 effectively fixes short query vector bias using that metadata optimization layer we discussed. Moving to 1.1.0, the architecture abstracts out a multi-client interface for Quadrant and Milvus. By version 1.2.0, the system introduces horizontally scalable ingestion worker pools to handle heavy concurrent document parsing. And finally, hitting version 2.0.0, the system integrates LangGraph to support fully autonomous, stateful, multi-agent workflows. It literally evolves from a single node pipeline into a highly distributed intelligence graph.
Which leaves us with this final, critical thought to ponder. How is your own infrastructure preparing for the inevitable shift to autonomous, stateful, multi-agent RAG? Honestly, integrating generative AI without breaking your current transactional systems is the architectural challenge of the decade. The OmniRAG project offers a really powerful MIT-licensed blueprint for how to bridge that gap non-intrusively. I highly recommend you check out the source material, review the code, and start thinking right now about how you can decouple your own data from intelligence. Thanks so much for exploring this blueprint with me on this explainer, and I'll catch you on the next deep dive.